Morning, everyone. So far in our intro section here, we've been looking at some of the math of chemistry. We've been learning the notion of significant figures, the uncertainty that we're limited by based on our interpretation, based on the equipment itself. We then did a detour through experimental error, which is the plus or minus. We talked about writing it as absolute errors, relative errors, and how that got carried through different calculations here. One key thing to take away here is we always round our finite errors to 1 sig fig, and we always make sure that it lines up with the guess precision on the measurement itself. Today we're going to switch gears a little bit here, and we're just going to talk about matter in general. Again, introduce some of the vocabulary. You will find this handout here also on the resources section here. A lot of this vocabulary you would have seen before. I just want to make sure that we're all on the same page as we continue onwards here. So if you can just print off a copy of the notes for yourself, and then you can just scribble over this one here. Let's have a look at matter. I pulled this from the regular grade 11 textbook here, so don't worry about it saying unit 3. But specifically what we're starting off with in this section is we're primarily looking at the notion of physical changes or physical properties. We will switch over into chemical changes, reactions, naming over the next couple of days or so, but for the time being we're just dealing with physical traits. So let's have a look at some of this vocabulary. We're going to start off in science here. Information can either be written to us as qualitative or quantitative. Qualitative here comes from the root word here, quality. The quality can be described without using numbers. Usually that's where we start. We make observations. The sky is blue. This table is hard. We actually are able to describe it without actually any number crunching. It's a qualitative, it's an appearance sort of description. Usually what we want to do is progress more so to a quantitative description. So that's where our next term comes in. Quantitative, it's based off the root word quantity. It's putting numbers to all that. When I said the sky is blue, maybe I pull out a spectroscope and actually figure out what particular wavelength, how many nanometers, is it 500 nanometers that shows this blue color here. When I said the hardness of the surface, is it a hardness of 10, hardness of 0, depending on your scale here. We want to usually go from qualitative to quantitative. Even though there is going to be an emphasis on quantitative, you will always want during a lab to list some qualitative observations, some things that may help you explain your numerical calculations later on. In chemistry here, we are concerned with matter. So here's a nice definition for chemistry. It's a science that studies the properties of matter. So sort of what are the characteristics, what are the traits. We're going to find that those characteristics are a direct result on the composition. What are the elements that make it up? How are things bonded together? How can I actually engineer chemicals and mix chemicals in different ways to actually have other macroscopic properties? We're basically focusing primarily on matter. So you've learned from your junior science classes here, matter is anything that has two things. It has to have mass and it has to have volume. So imagine I have a gold brick here. Basically the understanding is if I had a sharp enough knife, I would imagine that this gold brick is made out of the Greek philosophers would call it atomos. Atomos would be the root word for atom, a small particle. Take a sharp enough knife and you can basically chop this up here. You can eventually get to a tiny atom. That tiny atom here has mass because it is made out of substance, it's made out of material, and it also has volume because it occupies space. This is a solid, the particles are just vibrating in place here. Space that's taken up by the solid cannot be occupied by other objects unless you take it away. So that's what matter is, that's what chemistry is studying of. Also some key things that aren't matter that also come into play when we do more physics and chemistry is energy. So energy is not something that has substance to it, so it doesn't actually have matter or material to it. Usually we talk about, let's say, light as photons of energy. You can make a note to yourself here. Something that is not matter, just as an example, could be energy. Photons are described as packets of energy as in contrast with particles of energy. We've introduced these terms here previous, physical change or chemical change here. Like I mentioned with qualitative earlier, physical traits are things that you can observe. The key feature for physical is that there's nothing new that's made. No bonds are broken, no bonds are forming. Things like the color, the hardness. If I take a piece of paper and I end up ripping it here, sure, the piece of paper is now in two, but I have not done anything to the chemical mixture that actually makes up the paper. So that's a physical trait, physical characteristic. While a chemical trait here is something that undergoes chemical change, bonds breaking, bonds forming, and it actually does change into something that's new. So for example, let's see if I can do a balanced equation here. Hydrogen burns in air, produces water. Hydrogen, we're going to see it's unstable by itself, so it actually comes to us diatomic whenever it's elemental. Hydrogen burns in air. Don't say plus air or plus fire, plus burning. The chemical that we need for burning is actually oxygen. Oxygen is also one of those diatomics. We'll go through all this in the upcoming lessons. And basically it ends up producing water. Even though burning, we expect it to produce carbon dioxide, maybe some carbon monoxide as well. There is no carbon source going into it. So in this case here, we only get the water product. We know something is off based on our conservation of mass. Hydrogen is sort of 2 red atoms. Oxygen I'm going to draw as 2 green atoms. Later on, I only have 1 green atom and 2 red atoms. What's off here is it looks like one of the green atoms has vanished. Now, I know atoms are very tiny. We're not talking about, oh, I just lost sight of it. There's something in science called conservation of mass. Whatever mass my reactants have to match up with the mass of the products. It is tempting to come along and change the numbers. Oh, what would solve the problem is make it H2O2. Let's put that green atom back. In fact, we can't do that here because chemically speaking, we actually form water. Our thing that solves it and fixes this here is we can actually balance the equation. Sure, my recipe involves mixing hydrogen and oxygen together and making water. I can balance it with coefficients, numbers out here to make sure I scale the numbers so that the numbers end up matching up. So the problem was I may need 2 waters. That way I would at least get 2 green atoms back. In that case there, whoops, I screwed up the red atoms. Let's put another 2 over here. Numbers that are not written, chemists are super lazy. If it's a 1, they just leave it blank. But do note that it's a 1 there, and we'll get back into this in terms of balancing. The 2 next terms here are nice if you want to sound fancy. These qualitative characteristics here can be either extensive or intensive. Extensive by definition is one that depends on the amount. It depends on how much is sitting in front of you. So mass and volume are good examples of this. Let's take a small ice block, little m, big ice block, big M. The number for mass is different because mass depends on what's sitting in front of you. Same as volume, small ice block, little amount of room. Big ice block, big volume, changes. What about intensive quantities? Intensive quantities are more so talking about the nature of the chemical itself. It does not depend on the amount. What would be the same about the small ice block and big ice block here? Let's take a look at melting point. So this is the temperature when solid becomes liquid. Don't say temperature to melt. You try to define it without using that term inside. When does this ice block melt? Well, 0 degrees. When does this ice block melt? Also 0 degrees. Because melting temperature here is actually an intensive quantity, whether it's small block or big block, that number is actually the same. Now, for sure, heat is actually extensive. It's going to take way more heat to actually heat up the big block to melt all those water molecules, but at least at 0 degrees, at that one uniform number, it actually does melt at the same time. Surprisingly for density here, density is described as mass over volume. Even though both mass and volume, both of these are extensive, turns out density is actually an intensive quantity. Not always, but in this case it is. So in this case here, if we take small amount of matter divided by small volume, that ratio actually is the same as, sure, bigger mass, a bigger number on top, but it's also equally well taking up more volume. If I do that ratio, density is always intensive. So if you want to just sound fancy on your labs here, you can say, oh, this is an extensive quantity, this is an intensive quantity. Intensive quantities are nice because they don't depend on amount. You can actually use them to identify, tell me what the nature of the substance is. Tell me what chemical it is. If I have a chemical that melts at 0, I'm leaning towards it potentially as water. We're going to come back in chapter 5 to take a look at more enthalpy, exothermic kind of reactions here. But what it's looking at is kinetic molecular theory. Basically the idea that everything is made out of tiny particles, everything has kinetic energy, everything has moving energy, and depending on the state of matter that I'm actually in, I'm either solid, bracket S, bracket L, bracket G for liquid and gas, and I've described for you the rigidity, it takes the shape of the container, it spreads far and fast for a gas. Those are the 3 most common states of matter. We're going to add one more, bracket AQ. Bracket AQ actually just means something that's dissolved in water. We're actually here talking about a mixture. So for example, if I take table salt, NaCl starts off in the solid state. We're going to drop it in water. Water is going to come in and separate the Na from the Cl. I can label this one here. NaCl, once it's in water, I can label it AQ because the NaCl is actually dissolved in water. In fact, we're going to see a reaction where Na becomes Na plus aqueous and Cl minus aqueous. I just use that as a label because it's dissolved. If it's pure, we wouldn't use the term aqueous. So some other qualitative characteristics here you can look through in more detail. I'm just trying to highlight some of the main terms. These values here are actually all intensive quantities. These ones here, if you think about it, it doesn't depend on how much material it is, it just describes the substance itself. So hardness, if I have a rock here, we scratch one rock here on a metal plate, let's say, whichever one here leaves a scrape here, usually I interpret the scrape as the leftover material left behind by the rock, then I would say that that bottom part is harder than the rock that I'm scratching. Malleability and ductility here are very common for metals. Actually, a lot of these are common for metals. Mallee, I always think of the word mallet, like a hammer. If something is malleable, if you take a hammer to a metal, you can hammer a piece of metal into a nice sheet, into a nice foil, or they're sort of flexible in some sense. If you pull at a piece of metal here on two ends, you can actually stretch into nice wires here. That's called ductility. So metals in general have this property. We'll look at metallic bonding and figure out why that's the case. Some metals are more malleable, less ductile, things like that. Lustre here is a fancy word for shininess. So this is how well it reflects light. Something that has a good lustre is it reflects well. If it's dull, it's something that has a really poor lustre. Viscosity, like honey, is a very stickiness to flow here. And we talked about temperature changes here. Melting point, I said melting point of ice, melting point was 0. When does water freeze? You'll also notice freezing is also at 0. This is for water at our regular common pressure. How do I know it's melting or freezing? Just depends on whether I'm adding heat or whether I'm taking away heat. At least the temperature itself is the same. If I add heat, things go from solid to liquid. If I then remove heat or cool things down, it goes from liquid to solid. As you get into the next section here, what we're going to do is we're going to start separating matter into categories. So matter comes to us in a whole bunch of different various forms here. We have a nice little concept map. Hopefully you can see it better on your diagram. We're going to have matter in the top, things that have mass and volume. Normally in your junior science table, they sort of skip this first state and they just go right into, oh, matter can be separated into pure substances, or matter can be separated into mixtures. This diagram here does one extra layer, and it uses the language of things that are homogeneous or things that are heterogeneous. If something is homogeneous, it feels like one material. Think about waving your hand in the air. You know your hand is running into carbon dioxides and oxygens, but it's not bumpy. It just feels uniformly mixed up, fully dissolved, homogeneous. Most mixtures, because they're made out of many different parts, most of them are not homogeneous, but it turns out one type of mixture that is homogeneous we'll talk about is called a solution. Most of our mixtures, because they're made out of multiple different parts, we call that instead heterogeneous. Heterogeneous meaning it's made out of multiple bits. Sometimes you can see all those many bits. Sometimes they're fully mixed together. It's more like a suspension. We'll deal with that a little bit later. The system for us in chemistry, the system is going to be the reaction. It's going to be the particles that are actually colliding. That's the part we're actually studying. We take the whole universe and we just look at the system. Everything else around is going to be your surroundings. I don't really care about what's happening outwardly. This gives rise to some interesting sort of heat changes. Like I might have energy conservation in the entire universe, but because my system is focusing just on these exact chemicals, maybe I have an exothermic reaction that gives off heat. Oh no, I've lost heat. As long as the surroundings pick up that very same amount of heat, the overall amount of heat stays the same. So that's where we deal with the notion of system and surroundings. We'll get more into it in chapter 5. Let's go down those two branches then. So again, traditionally we separate them either pure substances or either we have mixtures. For a pure substance, as the name suggests, it's pure. It's made out of one type of material. It's homogeneous. It feels like one phase. It feels like one material fully mixed up, and it's unchangeable. Under the category of pure substances, surprisingly, we have two categories. We have the terminology here, element and compound. For these two words here, I think of the keyword here, type. Our periodic table, the full name is actually the periodic table of elements. So if I find an entry for it on the periodic table, let's say lithium is sitting over here, I have neon is sitting over here, every one of those has its own atom to it. Silver is an element, it has an atom. Copper is an element, it has its own atom. Hydrogen is an element, it has its own atom. The type of it is actually different. In chapter 2, we're going to come back, look at different models of the atom. We know that the difference is actually the atomic number, the number of protons, but something is fundamentally different about these atoms themselves. Surprisingly though, when we then switch over to the word compound, a compound is actually made out of more than one type. Well wait, if I have more than one type, doesn't it make me not pure anymore? The key feature here is, sure, I may have more than one type. I may have taken more than one of these elements on the periodic table, but because they are bonded together, because they are always grouped together, they always hang out together, we're going to cheat a little bit and we're going to say, as long as your whole container, methane is a common name I want you to memorize. Methane is our fuel for Bunsen burner natural gas, so CH4. As long as my whole container are just blobs of the CH4, we'll come back in chapter 4 to predict all this bonding and the shapes, all that variety here. But as long as my container are just CH4 blobs, yes, a C element is different from an H element, but because they are bonded together, that's a blob of CH4, this is a blob of CH4, they all are sort of grouped together. We're going to still refer to it as pure, as the whole box is containing CH4. When does it stop becoming a pure substance is, let's pump in ammonia, another common name here. Care for the ending. Later on we'll see ammonium, which is NH4+. Ammonia is the neutral molecule. If I now pump in extra NH3, NH3 by itself is a compound. It has the N type and the H type, but because they hang out together, they're pure. But my ammonia is not actually bonded with the methane. In that case there, that definitely is a mixture. So that's when we actually do the lens of homogeneous or heterogeneous mixture. Let's skip down here to the bottom. We can then identify atoms, molecules, and ions here. For atoms and molecules, I refer to that in terms of number. I don't care the type of material anymore. This time I just care how many. In this case here, we said atom is the smallest unit of an element. Every element has a unique atom with its unique number of protons. A molecule is also a cluster that's bonded together, but in this case here, it's just a cluster of more than one. I don't care if they're different. I don't care if they're the same. So what we're going to have here is, let's take a look at the methane molecule, CH4. Because I have more than one type, we are definitely a compound. I'll just write CPD. We're also a molecule because I have 5 things that are bonded together, molecule. So in fact, all compounds, because they have to have at least more than one type of element, all compounds are molecules. However, let's take a look at the hydrogen from earlier. Let's say the H2. The H2 is a molecule. It is going to be one atom connected to another atom. More than one type bonded together makes me a molecule. However, if we look on the periodic table, wait, this is just the H kind of material. This is actually just an element. So although all compounds are molecules, not all molecules are compounds. We generally say atoms and molecules here, these are going to be electrically neutral. We're going to see it's because protons are matched up with electrons later on. When we start doing bonding, when we start changing the number of electrons, I can gain electrons. As I grab things that are negative or being reduced, I become an anion. I become a negative charge. I have more negatives than positives. If I lose electrons, we call that process oxidation. Metals tend to get oxidized. They tend to take on a positive charge instead. So assume atoms and molecules, sometimes they're redundant. They say neutral atom, neutral molecule. Those already mean neutral. But especially when electrons start getting transferred around, we actually start getting charged particles. Let's just also talk about mixtures before we go to the backside. For mixtures, when things aren't bonded together, there's actually 3 types of them. Mechanical mixtures are the one that you're probably thinking of. If you're made out of multiple different types, you can probably see all the bits. So in this case here, there's variable proportions. Gravel will be a combination of cement, rocks, dirt, you name it. Okay. So mechanical, you can see the bits. Pizza is a mechanical mixture. A solution is down the line. It is actually homogeneous. If you go down to the pier and you grab some ocean water, it looks completely clear. And yet when you drink it, you realize, wait, it's really salty because those salt ions are completely dissolved, fully mixed in. So that's a solution. We're going to come back and we're going to talk about concentration to figure out how much chemical is actually being dissolved. What I want to introduce to you for this one here is actually the word suspension. A suspension is somewhere in between. You can sometimes see that it's one material. You can sometimes see the bits here. And examples of this here is tomato juice, or let's say we go to a Japanese restaurant and we have miso soup. When they first bring out the miso soup to you here, they may have just recently stirred it. Basically, all the little miso chunks, tofu chunks, and veggie chunks here are actually all swirled up. They're temporarily suspended. They feel like one material. Over time, however, because those parts are more dense than the water around it, over time they end up settling out, and in that case, you can definitely tell it's a mixture. So suspensions are basically temporarily, if you agitate the mixture, you can temporarily get the particles swimming around. Finally, onto the backside here, especially when we start talking about mixtures, it's a little bit hard to study chemicals when they're all mixed together. What we want to do is we want to actually separate chemicals so that we can study the different bits. I'm not going to be testing you directly on any of this stuff here. These are just some nice key terms as you just think about general techniques. How do we separate chemicals? Next year when you actually do your IA, you might consider doing these separation techniques here. And would just use this as more like a reference chart here, looking back based on what mixture I have, what tools do I have, techniques do I have to actually separate them. So let's just do a section on separation methods here. So separation methods. We're going to start off super simple here. These are all physical traits. So these are all, they don't change the chemistry, they don't change the bonding of the chemicals. These rely on different characteristics. We're going to see boiling point, we're going to see density, physical characteristics that we can leverage to separate them. So lots of detail here. I'm just going to emphasize some of the main bits. We can do hand separation. So if I have a mechanical mixture, when I can see all the bits, if the parts are actually visible by eye, let's say I have a container full, I have some golf balls that are smaller, I have some tennis balls that are larger. If you had the time, you can just by hand, you can say, oh, that's a tennis ball or that's a golf ball. You can do that to separate it because they have very different sizes. So in this case here, difference in size. Even though it's called hand separation, it doesn't necessarily mean you actually need to use your hands. So for example, if I was boiling a pot of pasta, I may have sort of pasta, spaghetti sitting in water. I would just pour it through a strainer. Because the pasta are nice long strands, those strands here get left behind. We're going to call that the residue. The water, which is a much tinier molecule, it's also in a state of matter, which it actually goes through the pores here. The water would then be separated. This is again a separation technique based on the fact they have different size. This next one here is interesting here between iron and steel. Iron is magnetic and steel is not. So if I have a bed of nails, I move a magnet over top of it. The ones that magnetically stick, I know they're made of iron. The other ones, stainless steel, aren't magnetic. Let's do this sort of hand separation method more in the chemical context. We use the lens here of filtration. Filtration basically does this past the water analogy, but we know the chemistry that we're talking about is the particles are going to be much smaller. If you just took, let's have a mixture of sandy water. So I have sand and water. If we pour it through a typical colander, typical strainer, those sand grains, like the water, are going to be too tiny. They're just going to fall all the way through. What I can do then is I can just, get a better strainer. Get maybe a filter paper here. Even though the filter paper might actually feel like it's solid, it's actually embedded with a whole bunch of tiny little pores, tiny little holes. Filter paper is actually graded with different size pores, and as long as the sand grains here are larger than the pores letting through, the sand grains will be trapped as a filter on the filter paper as a residue. The part that gets through the filtration is called the filtrate. So works for undissolved material as long as the molecule size is good. Another way of doing it here, if it was undissolved or even if it is dissolved, usually relying on boiling point. Let's say I go back to my saltwater analogy here. Those salt grains here have formed a solution. The salt grains are fully dissolved, and basically my heat source ends up boiling things off. We're going to find that in general, the solvent water, the background, actually boils off much quicker than these salt grains themselves do. So by evaporating, sure, we end up, the downside is losing the water, but we'll end up, if you ever grown in crystals, that's actually what we're doing there. So we manage to separate the water. Water is relatively inexpensive, so I'm not too worried about it actually leaving. If the solvent was actually really expensive, I don't want it literally evaporating on me, boiling off on me. So what we're going to do is we're going to, for dissolved materials like salt water, we can actually couple it through a distillation setup. Distillation is how they, let's say, purify gasoline when they dig it out of the ground. They purify wines with distillation as well. The key feature here is we are separating based on different boiling point. Based on the chemicals here, they actually boil at different temperatures. Some boil quicker, some boil slower. Let's say I have a mixture here. Your pictures will look a little better. Let's say I have a mixture of A and B. Just like the water and the salt crystals that actually boil at different temperatures, let's say I only heat it enough so that A can actually vaporize. Earlier for evaporation, we were in an open system. Those gases just escaped. This time what I'm going to do is I'm going to shunt this hot gas. I've only heated up enough so A escapes. I'm going to run it through this tunnel. And what I'm going to have is a condenser that is actually running cold water on the outside. The cold water actually just provides a nice cold environment for this hot gas to travel through. As a hot gas runs into a cold environment, it ends up condensing. That's why we call it a condenser. And as a liquid, we can then collect it. If it's gone through a distillation setup, it's now called a distillate. Now, after all the A is gone, I can remove the beaker, put a new beaker in, I can heat it up some more, and I already have B. That works on the fact that they have different boiling points. Again, all of this one here, just use it as a nice reference sheet here. We do all these techniques really common, but I just want you to be just familiar with some of these physical techniques. The next one here, let's say the two chemicals unfortunately have a similar boiling point. So if I run it through a distillation setup here, unfortunately it doesn't separate A from B. There are other chemical techniques that rely on other physical characteristics. Here's solvent extraction here. This is actually based on different solubilities. Solubilities actually talk about the ability to dissolve. We usually assume dissolve in water, but in chemistry we can dissolve it in nonpolar substances like petroleum ether. We can deal with many different chemicals. So let's say I have this AB mixture. Unfortunately, they boil at the same temperature. So if I try to do distillation, unfortunately both A and B would vaporize at the same time. I wouldn't be able to separate one from the other. What I'm going to do with a solvent extraction, it is a sort of liquid-liquid extraction here, or a solid-solid, even if you want to do that. In this case here, what I'm going to do is I'm going to add a third liquid. There's two criteria for this, second liquid. There's two criteria to this liquid that I add. The one criteria is the liquid has to be immiscible. Like oil and water, which we're going to see in chapter 4 as nonpolar and polar, they need to naturally be able to separate. Polar things here are like charges, nonpolar doesn't. So even though temporarily you might be able to mix them up together, they're going to naturally separate into two different layers. The other one here, the other feature for this liquid that I add is the fact that they have to be able to preferentially dissolve one substance. They have to be able to dissolve one substance better than the other substance. So imagine with me here, I found one of these liquids. I'm trying to mix up A and B. I add a fresh solution of this liquid here. Let's say for argument's sake here, it dissolves A better than it does B. In that case there, you shake it around a little bit here. You have a stopcock that you can open and close. As you shake it around, these liquids here temporarily get mixed. You allow the A to actually dissolve into the liquid that I added. You let it settle. You let the immiscibility separate into two different layers. What you're going to have is still a lot of A in this bottom layer. You're going to first collect this first beaker. That's going to be a mixture of A and B. And then when we collect, once that solution has run through, now you can collect in another beaker. This is now just pure chemical A in my new liquid. Now that I have a mixture of AB again, I can shunt it through the same flask. I can add some fresh new liquid again, shake it around again, and basically I can end up picking up more and more and more, and I can just collect out the A. Hopefully what's remaining then is B. The analogy here is, let's say I just wash my hands. In terms of drying my hands, I can take 3 paper towels all at once. Sure, I'm going to get my hands to a certain level of dryness, but what if I did it successively instead, one by one? I took one piece of paper, I dried my hands, took another piece, dried my hands, take another piece, dry my hands. Each time I take a piece of paper, I end up drying my hands a little bit more. Just like in this case here, each time you run it through a solvent extraction, you end up managing to pull it out more and more. They've done calculations of this. Even if the separation is only about 90% successful on a time, or even, I think even lower than that, maybe 60%, 70%, by the time you've done 3 of these extractions, you manage to pull up about 90% of the material. So that's called solvent extraction. That doesn't rely on boiling point. That instead relies on different solubilities. They do a sand and salt analogy as well. You can read through. Basically, when you add water, the salt dissolves. It preferentially dissolves, but the sand doesn't dissolve. So in that case, we can just filter off all the water and leave the sand behind, and therefore we've done solvent extraction. This recrystallization method here isn't overly clear here, but basically the idea is usually in, especially organic chemistry, when we end up producing a chemical, we've gone through maybe 10 steps in order to create some crystals, create some chemicals. Unfortunately here, the chemicals that we created here could potentially be impure. So what we're going to do to try to separate off those impurities is we're going to purposely dissolve that material again. Well, wait a second. I just went through so many steps to actually create this chemical. By dissolving it once more, I'm giving it one more chance for the chemical to actually separate from some of the impurities. And then what we're going to do is we're going to recrystallize it. We're going to then maybe boil off all the water. And then now, because I gave it another chance to actually reform the crystal, as the pure chemicals actually form their formation, they're going to actually push out other impurities. So that way is also a separation technique very commonly used for organic chemistry. In fact, if it's a pure substance, all the heat that I add to melt it should be used just to break up the intermolecular forces. The temperature should actually be level as you're breaking up, as you're changing the state. In fact, in organic chemistry, we can actually figure out if there is some range in melting point. We were supposed to melt at one unique temperature, but if I'm melting over, I happen to start melting and I end melting 5 degrees later, the higher that melting point deviation is, that's actually a nice measure of how impure the substance is. We can do 2 other separation techniques here. One is gravity separation, basically using separation based on different densities. So imagine I went to get a blood test. The blood is a solution. It's made out of different blood cells, different platelets, all different densities. We run it through a centrifuge. It's a device that spins around really, really quickly. Based on that spinning motion, the heavy, dense particles end up coagulating at the bottom, and we end up getting just a liquidy yellow plasma layer on top. So that one there is using a centrifuge based on different densities. The next one here is interesting. We can run it through a column. Chromatography can be done either with a paper or a column chromatography. Hopefully I'll be able to do this lab with you here. Basically, we're going to have a strip of chromatography paper. It's a special type of paper that has these little pores and little tunnels that if I drop in a layer of water, the solvent, the water can actually climb up these pores here. I'm going to have a tiny drop of, let's say, green food coloring here. Because food coloring here is soluble in water, this one also relies on solubility, what's going to happen is green is going to dissolve in water, and it's going to steadily climb up with the water as it climbs up this paper here. It's just that green is actually a mixture of a blue chemical and a yellow chemical. Because the blue and the yellow don't dissolve at the same rate in the water, let's say blue dissolves really well, it's following the water really well, the yellow is sort of dragging its feet a little bit here. The longer I let the race run, the more the blue is going to separate from the yellow. So the analogy there is, let's say I have a race that I'm watching. I have a fast runner and a slow runner. They all start at the same starting line. As I say go, these ones here start running. The runners that run really quickly will run sort of neck and neck with the fastest time here. The ones that are a little bit more sluggish and slower, they're dragged behind. The longer this race here drags on, the farther apart the fast runner and the slow runner is going to be. Eventually, I'm going to be able to collect just the fast runner and just the slow runner. The problem with doing it with paper chromatography, unfortunately here it's all qualitative. All these chemicals here are embedded, absorbed onto the paper. We can actually run this racer upside down. I can have my stationary phase. I can have basically an obstacle course laid out for this green food coloring. Have some green food coloring here. This time I'm going to naturally pour water through, and water is going to slowly dissolve that same green food coloring. Same idea. The blue food coloring, for argument's sake, here is going to run faster. The yellow food coloring here doesn't run quite as fast. So the first ones that make it through the obstacle course, the race, I'm going to collect up just the blue. Eventually, once all the blue's gone, I keep tossing in more of this mobile phase here. Eventually, the slower runners also make it out, but just do make sure to collect it in a separate flask here. And now I have actually made solutions, not just separated, not just qualitative observed. So those are some separation techniques. Again, I'm not going to test you directly on any of those names, but you do want to have some familiarity. These are some physical traits that I can leverage to actually separate the materials. To finish off our lesson here, we talked about already physical and chemical changes. Chemical is the whole notion making new substances, breaking bonds, forming bonds, whereas physical changes is no new substance being formed. One last good example of a physical change when the chemical itself actually doesn't change is the whole notion of a phase change or physical change. So let's actually start on the bottom here. Let's imagine this guy here is called the temperature time graph. Hopefully you have the whole plot for you here. We're going to start off with ice, which is H2O solid. That's water particles that are just vibrating in place. As you steadily heat it up, there is some unique temperature called the melting temperature, intensive, that basically it's heated up enough that all the heat that I'm applying is actually used to rip apart the structure, is to separate the water molecule. Eventually, when water is a liquid, we now can slip and slide past each other, a little bit more kinetic energy, but you notice chemically speaking, we are actually still the same water, although we're liquid. We haven't broken any bonds or formed any bonds here. This was a physical change. So make a note here. A phase change is a physical change. The reason why we're going to call this, we'll come back to this in chapter 5, the reason why the temperature plateaus, you are actually adding heat. Temperature plateaus because all heat is used to change. You can say change the state to be generic, solid, liquid, and gas. Sometimes for solids, they're bonded in different ways. They prefer the language of change phase. So I can have ice in phase 1 or phase 2. It is still solid, but depending on the formation, depending on the angles, it may actually look different. All that heat is actually used to change the state instead of changing the temperature. That's why it should be one unique temperature that it melts. Obviously, experimentally, maybe I do this on a hot plate here. There's no guarantee that the hot plate heats up this ice block here all at once uniformly. I may heat up the bottom parts a little bit more, so maybe this plateau here might actually be more so a curve. We mentioned that earlier here. If it is more so a curve, any deviation could be this heat transfer problem. The other reason could be of some impurities. As you add heat to it, let's focus here on water. It is going to be a physical change. Basically, when let's say I microwave foods, microwaves are exactly the right energy for water molecules to actually dance around faster. And as they dance around faster, it actually causes the temperature that I sense to be a little bit hotter. So when we think about kinetic energy, think about energy of motion, as they stick in the microwave, we normally just think about, oh yeah, if you heat things up, things move faster, they slide around faster. That mode of kinetic energy is called translational energy. I can slide to the right, slide up, slide down. No twisting or anything like that. Just moving faster, just sliding around faster. There's actually two different modes that a molecule like water can actually absorb this radiation. It can actually rotate along the axis. So there's an axis here, let's say up and down through this oxygen. It can rotate around the axis. As you heat this water molecule, it can just twist around faster, twist one way, twist the other way, rotate, flip this way. It can even do this sort of twisty motion going up this way. The last way here, another mode of kinetic energy here is actually vibrational as a mode. Even though we draw these sticks here, it sort of looks like the bonds are solid. We can actually think of more so these electrons that make up the bond as little springs. Naturally, these bond lengths here, some arms are longer, some arms are shorter. And by heating it up, we're going to actually start going longer, shorter, and we're going to stretch a little bit quicker. Even the bond angle, we're going to qualify the bond angle as about 104 for water here. The bond angle can shrink. It can go 100 degrees, 110 degrees, and it can stretch and contract. As you heat water, we are increasing the overall kinetic energy. Lots of it does go to translational, but it also can go to it twisting around faster and it vibrating, the bond lengths shaking and the bond lengths stretching and contracting a lot more as well. So have another look over this page here. This is all physical changes. As we step to the next lessons here, we're going to switch over to more so the chemistry. Thanks, guys. Take care.